This talk is about how I made planets in the 1977 to 1983 time frame. When putting it together, I was actually able to dig out most of the original data and source code that I used so I could look at it to remind myself about how things worked. I'm calling the talk Magrathea because in about 1979, I was giving a demonstration of our system to a journalist from England, and he said, "Oh, this is Magrathea." And I said, "What's that?" And he said, "Oh, there's this humorous science fiction program on the BBC radio, and it has a place called Magrathea where they manufacture planets." Shortly after I got to JPL, I met Charlie Kohlhaas, who was the director of mission planning for the Voyager project. He and Paul Penzo have produced a series of line drawing animations showing what Voyager would see while going by Jupiter and Saturn. Most of these were lost, but I have a few brief clips here. So, seeing this, my purpose in life was revealed to me. I must make a similar movie, but in color with textured planets. Here's a brief clip from what I came up with. It shows the transit of the moon Io in front of Jupiter as Voyager 1 approaches it. So I'll be describing how this and other similar flyby images were made. I want to start off with a nod to the guy who hired me, Bob Holtzman. He had found funding to purchase a hardware system that was, conveniently, an exact copy of the equipment we had at Utah, and he supported me in doing whatever projects I wanted. So first, a description of the hardware. We had a PDP-11 55 computer with a 2 MHz clock and 128 kilobytes of memory, all in a room with lots of noisy cooling fans. Now, since the PDP-11 was a 16-bit machine, we could only address 64 kilobytes at a time. Basically, below 64K was devoted to the operating system, and the user programs had to fit in the upper 64K. Now, 64K is not a lot, and that was a big design constraint on the software system, but it turns out that it had some hidden advantage in system organization. Now, the cool thing about this was the two separate display peripherals we had. There was an ENS Picture System 2 that had hardware to generate 3D line drawings, similar to Charlie's movie, but his movie was done offline on a microfilm recorder. Our picture system could generate it in real time. The other device was a newfangled thing called a frame buffer. That was where we could display color-shaded images. A little about the frame buffer hardware. It consisted mainly of a 256 kilobytes of memory external to the PDP-11. Now realize that this is an incredible amount of memory for the time, comparable to a mainframe machine. It was all made with 1 kilobit memory chips, 2,048 of them. To access this, there was a dedicated 8K window of the PDP-11 memory, along with some control registers to give the extra address bits to tell it where to map window into the frame buffer. Simultaneously, there was a microprocessor that was continually scanning out the memory and synthesizing a video signal from it. Incidentally, the designer of this system was Jim Kajia. Anyway, each pixel in the memory was 8 bits, but that was used as an index into a 256-element color map. Each slot of the map had an arbitrary red, green, and blue value, so we could have any of 256 different colors at once in the final image. Now, it was nice that Jupiter and Saturn weren't all that varied in color scheme, basically black, white, and orange. So we used a color map that divided the 256 colors into 32 shades of 8 different saturations of orange. Now, 32 shades isn't really enough to give a smooth gradated image. So I applied what is called ordered dither to the pixels. You can see what that looks like zoomed in here, but back off and it looks smoother. You're basically trading some graininess for more effective intensity levels. Most of the images I will show here had this pattern in them. Let's go back to the Io transit image. It illustrates a rendering problem that is perhaps unique to space images. If you look at a side view of the geometry of the situation, you see that there's a tremendous range of distances in this scene. Io is that barely visible dot in the middle. The Voyager is about 10 meters in size and almost coincides with the eye at this scale. So considering that you want about 1 centimeter resolution on the parts of the spacecraft model to look reasonable, you get a size range of about 10 decimal digits, just for the size of Jupiter. Putting all the parts into one coordinate system would require a lot of resolution. We can avoid this problem using what is called a depth priority algorithm. Draw each object in its own coordinate system in order back to front. This fits into a software environment that I call the frame buffer synergy. The idea is that the operating system doesn't really know about the frame buffer. It doesn't allocate its memory. It just leaves it alone. So whatever you did with the frame buffer would stick around from running one program to the next. So we generated a collection of programs that did something to the frame buffer. Paint into it, save it to a file, read a file into it, overlay some geometric shape onto it. So we have lots of smallish programs, each good at one type of object. There's one program to draw a star background, another to draw spherical planets or moons, one that drew arbitrary polygon meshes to do the spacecraft, one called MISC that was to draw various miscellaneous dots and splotches, one that drew rings of Saturn, and so forth. All the programs interacted with the user via text commands. They all had a common command structure. You could run a program, type in commands, place the object, give lighting parameters, maybe texture file names, and then a draw command to draw the object. And they also had a read command to redirect input to a file, which, when finished, would return to the keyboard. This was recursive, and the files could have read commands to insert the contents of other command files into the program's input stream. This organization made the easier programs easy to debug, too. Let's start out with a central program called simply Space. This displayed its status on the picture system, so we could set up shots in real time. Now, it was important for me to get the geometry right for all the space scenes. The positions of all the bodies are calculated from data from the mission planning team using the osculating orbital elements. I really like the terminology names the astronomers used: Earth mean ecliptic 1950, first point of Aries, longitude of the ascending node, mean anomaly of periapsis. I cannibalized some code from Penzo to turn this into 3D positions of all the objects given a time relative to closest approach of the spacecraft. Simulating the Voyager spacecraft involved getting this orientation right. The axis of the antenna dish pointed at the Earth, and the Voyager rotated around that axis to point a sensor at the star Canopus. This was the default position. Also near the top, you can see the scan platform with a set of cameras on a boom that could rotate around 2 axes. I spent many hours testing my code to make sure that I was simulating this correctly, basically reproducing the software the mission planners used to design the camera timeline. So in addition to making images of the spacecraft with the planet or moon in the background, I could simulate views through the onboard cameras by entering the same 2 pointing angles that they were sending to the Voyager, or by typing in the name of a desired moon and having the program calculate the angles. Given that, I programmed it to project camera fields of view on the various bodies. You could simulate aiming the cameras by turning 2 knobs, and the field of view would flow across the sphere, sticking out if the camera view hit the silhouette edge of the planet. Charlie Colhase used this to generate some PR pictures before the Voyager 1 Jupiter encounter, showing what the cameras were going to see. To set up an image, you needed basically to tell the program where you, the observer, were sitting and what direction you were looking. The program had various view selection options. You could type coordinates in numerically, but that was hard to get good views. The most useful mode was where you could select an object to be in the foreground and where you wanted it to appear on the screen, and then select an object to appear in the background and where you wanted its center to appear on the screen. The program would then figure out the eye point and viewing direction that would make this happen. Also, there was a viewing mode where you could sit on the surface of a body at desired latitude, longitude, and altitude and look in a desired direction relative to the horizon. So you enter in all the values for the desired view and then give the command draw. The space program would then do a depth priority analysis. First, transform each object to viewing space, figure out if it was in the field of view, and if so, add it to a list. Then sort the list in the Z direction, and then traverse the list from back to front. It opened up a command file to contain the drawing commands. It would then do the stars. It wrote a file stars.temp containing a viewing matrix for the star background, and then wrote a command into the command file to later invoke the star drawing program. Then here next was Jupiter. Write out a jupiter.temp for the planet program with viewing and texturing commands for Jupiter, and add a line to the draw.command file to later invoke planet. Then if a moon or a body projected onto an image less than a pixel across, it would invoke the MISC program to just draw dots. Then here we have IO with its command file and drawing command. Then the spacecraft with its drawing command. Finally, it would transfer control to the system to execute the drawing commands. Each command would invoke the appropriate program and have it read in the appropriate drawing command file. And you could watch this program unfold before your eyes. Stars, planet, spacecraft. Now let's look at some of these programs in a bit more detail. First, the stars. I was able to get a star database from the Smithsonian Astronomical Observatory. It gave the right ascension, declination, magnitude, and spectral class of the 422 brightest stars. I drew each star with a 3x3 point spread function to give anti-alias dots. I had to fudge the magnitudes though, because using the true magnitudes would make the dimmer ones too dim. But by using real star locations, it enabled me to make this nice image of Io with the Big Dipper in the background. The miscellaneous program basically just did an individual dot of arbitrary size, but it also could draw an impression of the sun as seen from a distance. In later movies, I improved the sun representation somewhat. Next, the planet program. The conventional way to do this would be to chop the sphere up into a zillion little triangles, but we didn't have the memory space to handle that. Instead, I applied a typical graphics trade-off. Instead of many simple shapes drawn by a simple program, I used a more complex shape, a sphere. It basically had one primitive, a unit sphere at the origin that you could transform and scale arbitrarily. It operated by first solving for the screen space ellipse on the silhouette edge, and it would scan from top to the bottom edge on each scan line, solve the left and right extent, then iterate across solving a quadratic equation at each pixel to find the depth. transform that to unit sphere space, take some marked tangents to get texture coordinates. Another advantage of not using polygons is that there are no polygons. No matter how close you still get the correct sphere image. One of the things I wanted to do was simulate images through the Voyager camera. The narrow-angle camera had a field of view of half a degree, so it was essentially a telescope. To make this sort of image, you get numerical problems with quadratic equation, since you have both roots very close together and very far away. I won't go into a lot of detail here. I wrote a series of articles about this that are in the reference sheet. Another snag is that in some situations the projection of the sphere is a hyperbola instead of an ellipse. Again, my article shows how to deal with this. In fact, I also used the program to draw some explicit hyperbolas to represent the bow shock for a movie on Saturn's magnetic field. Also necessary is taking care to anti-alias the edges. For the pixels that were completely covered, I just sampled at the pixel center. But for those that are partially covered, I solved for the edge and put a pixel sample halfway between it and the pixel edge, then calculate the proportion covered and use that as a blending alpha value. This is a fairly crude approximation, but it worked pretty well. That part of the art here, finding relatively fast approximations to the theoretically perfect solution that look good enough to use. Next, a little bit about the texture maps. So the first Jupiter map I used was constructed from some early Voyager 1 images. I mentioned the narrow-angle camera was basically a telescope, so several months from the encounter, we were still getting images that were several hundred pixels across. Since I had a simulation of the spacecraft camera system, I could calculate what the viewing transformation was for each of those images and write an inverse texture mapping program that would scan through the texture map, transform it to the pixel in the image, pick up that pixel and put it in the map. Of course, you only got one side, so half the map. This is the result of 4 such unwrappings blended together. Then, using a paint program, I filled in the cracks to get a reasonable map for Jupiter to use for the Voyager 1 flyby movie. For the moons, we didn't have any data, so we hired an astronomical artist to draw our best guess at what the 4 Galilean satellites might look like. Here are the real images sent back by Voyager 1 of the Galilean satellites. This was too good. For the Voyager 2 movie, now I was able to use the same inverse mapping trick to get correct moon maps. First, a better Jupiter map, then Io, and Ganymede with a little artistic interpolation, and Europa. I couldn't find the Callisto map. Next program, polygon meshes for Voyager. First, the database. I started out with blueprints of the spacecraft, and I measured some parts with a digitizing pen, but mostly I just read off the numbers and typed them manually into a text data file. The renderer used the typical points polygons data representation. Here it is for the main bus. I included some medium-level primitives in the rendering program too. Here are some surfaces of revolution for the antenna dish. Voyager had a lot of tubes in it. Rather than model each tube as like 6 or 8 polygons going around it, I added a primitive that would take the tube endpoints and radius and calculate the 2 polygons that would represent the tube best visually. A lot of these tricks were to keep the polygon count as low as possible. Now the reason for these medium-level primitives is that since most of the modeling was done by typing in numbers rather than tracing out with a digitizing pen, any simplification was welcome. Now the rendering process. This is a fairly conventional algorithm at the time. There were 3 passes. First pass read in the database, generating and transforming and lighting and clipping all the polygons and placing them in a list. Pass 2 would sort the list by maximum Y. Pass 3 would then scan down the screen, keeping track of what polygons are visible on the current scan line. That's why you needed a Y-sorted list, so you could easily add newly visible polygons with each incrementation of the scan line. But 64K, I could only fit about 100 polygons into the program. So for Voyager 1, I used 2 models. One had all the stuff on the backside commented out, and we used this for the first part approaching Jupiter. Then for the part exiting, I uncommented the backside polygons and commented out the front side ones. Later, I split the polygon renderer into 3 separate programs. First pass wrote out the polygons into a file as it processed them. Second was just a small program with a big array. It would read in, sort on Y, and write out again. This got my polygon count up to 1,500. The third pass would scan out the image, reading the polygons as needed. So here's a bit of the Voyager 2 dancing around as it approached Saturn. You can see the scan platform motion, and then rotation to a plasma scan. These motions all came from Charlie Cohase as the actual mission plan maneuvers. I also used the polygon program to draw Mimas, starting with images sent back by Voyager 1. After texture unwrapping, it was clear that simple texture mapping wasn't going to cut it for showing the giant crater on the equator. So first, to generate a relief map, I tricked out a version of the paint program so it would put a cursor on the bottom of the screen, but draw into the top part. So I traced out the crater with a dark airbrush, then traced out the peak with a brighter airbrush. This gives what would serve as a bump map, but that still wouldn't be good enough. Instead, I wrote a program that would generate a polygon mesh sphere and add in the appropriate amount of the texture value to displace the mesh points, and it could spit out transformed polygons directly in Y-sorted order, then run py3 on them to draw the surface. I used this as the introduction to the Voyager 2 Saturn movie in 1981. Several years later, somebody else rediscovered the idea and called it displacement mapping. Next program, line drawing. It's a fairly simple program, transform textured anti-aliased lines, used, for example, to overlay footprints on the images. But I use them for other things too. Voyager 1 found volcanoes on Io, so I needed to do something to simulate them for Voyager 2 movie. I generated a simple procedural model using textured lines to give us somewhat the impression of spewing stuff. I got all the locations and sizes from the mission team. This looks a little bit cheesy, I know, but it was the best I could do at the time. It was sort of a precursor to particle systems. Likewise, a similar procedural model of streaks for some ring particles as we cross the ring plane. Speaking of rings, Pioneer 11 went by Saturn in 1979. So to make a movie of that, I needed to draw rings. The basic idea is to scan out each pixel inside the elliptical outline, project back to find the location on the ring plane, find the radius from the center, and look it up in a 1D texture table. I got a texture from some Earth-based images of Saturn. I measured the brightness as a function of distance from the planet, and used that as a transparency applied to a uniformly white ring. Here's the 83 points I used. Now to draw this with a depth priority algorithm, I needed to split the rings in two. The ring program would draw half the rings, split at the silhouette plane of the presumed central planet. Flag would select first the back half, then run the planet program to draw Saturn, then run the rings program again with the flag set to draw the front half. This looked pretty neat for the Pioneer 11 movie, but there are two things wrong here. One is the lack of a ring shadow, and the other has to do with how the ring particles actually reflect light. I did some studying up on physical models of light reflection through the rings and was able to adapt the published models for computer graphics use. Basic idea was the more particles per unit volume there were, the brighter and more opaque the rings. But that was only if you were on the lit side. If you're looking through the rings from the unlit side, the brightness would start falling off with particle density, since the rings were blocking light now. It was also described in a paper in the references. So here's a trip through the rings from the unlit to the lit side, also showing the ring particle streaks at the crossing point. In addition, I was able to use some star occultation data to get higher resolution particle density readings, about 480 points. This, combined with the ring model, gave a database that gave particle density and particle albedo as a function of radius. Now, most views of the rings are nearly edge-on, so anti-aliasing the rings was important. At each pixel, the program actually calculated the radius at the four corners of the pixel square, found the minimum and maximum of those four radii, and averaged the texture across those radii. And it was smart enough to share the calculated radii with the neighboring pixels. And now for a quick diversion about shadows. The first shadow rendering I tried was only good for distance shots. It would run a line from the sun to the moon and intersect that line with the planet. If the intersection existed and was on the lit side, it invoked the miscellaneous program to draw a black dot on the planet. These examples are a bit subtle here, but you can maybe see a shadow on the middle of Saturn. The advantages of working with a few simple geometric shapes is that explicit shadow calculation is easier. For example, to find the shadow of Saturn on its rings, you click like the cone from the sun tangent to Saturn, intersect that with the ring plane, getting an ellipse, project that to the screen to get another ellipse, and then as you shade each pixel of the rings, test to see if it's inside the shadow ellipse and on the night side of the planet. By the way, the shadows and night sides of all the planets I've shown here would normally be totally black, but I made them have a little brightness to make the images more understandable. Conversely, to get the shadow of the rings on the planet, I calculated a line through each of the pixel corners to the sun and intersected them with the ring plane, giving 4 radii. Take the maximum min of those radii and integrate that over the transparency of the ring. Some early exit tests were done to only do this calculation on the planet pixels where the shadow actually hit. Finally, there was an experiment on Voyager 2 that tracked one of the moons of Saturn as it went into eclipse. For each pixel of the moon, the shadow amount was calculated from the proportion of the sun's disk that was obscured by Saturn. Here we see the moon going into shadow with the field of view of the photopolarimeter around it. Back to the rings, Voyager 1 found a very faint ring around Jupiter. Here's a simulation of that with exaggerated brightness. And some Earth-based star occultation data found similar dim rings around Uranus. Here's a plot of the ring radii that I got from their published paper. And from the Voyager 2 Uranus movie, I eyeballed which frames of the movie each ring included the sun, and re-rendered those frames with the sun dimmed out, giving a correct rhythm of blinking. But the neatest database came from the Voyager 2 Saturn encounter. It did a star occultation in situ on the portion of the rings in shadow, here brightened for visibility. This generated 20,000 data points. Now doing anti-aliasing here will be a computational chore because the ring radius range of each pixel might have several hundred samples to average over. So I used a trick I learned from Frank Crow from his thesis. If you're going to average over a large range of samples of a function, rather than store the samples, store samples of the integral of the function. Then the sum of any range of values was simply the difference of the integral at the endpoints, one subtraction. Now at this point I had a VAX with 2 megabytes of memory, more than anybody could possibly need. But although it had room for 20,000 sample ring texture, adding them all up would cause some precision problems. So I subtracted off a linear bias from the integral function to keep the numbers reasonable, and then added in the difference to get the proper integral. So here's a flyby of the rings of Saturn, designed by Charlie Kohlhase using the 20,000 sample ring texture. So that's the state of things in around 1983. If you want to see the articles that I referenced in the talk, take a look at jimblinn.com/Magrathea.